Hey everyone, welcome back, and let's write some more neat code today. So today let's solve binary tree level order traversal. It's basically just like it sounds, so we're given a binary tree and we want to return the level order traversal of its nodes. So basically going through every single level of the tree and going from left to right. So for example, for this tree we have this level, so that's going to be one list. We have the second level, 9 and 20, and then we have the third level, 15 and 7. So we have 1, 2, 3 lists, and these lists are going to be put together, and that's going to be our result, the 3 lists in that order. So to understand what we want to do is pretty straightforward, right? So basically we have the first level, right? Go from left to right. We see that there's only a single node in this level, 3. That's going to be one list. We see the second level, right? That's what we want to do. We want to traverse this tree every single level, right? One level at a time, going from left to right. So the second level, we'll see 9 and 20, right? We want to add that to a separate list. And lastly, we'll get to the third level. Going from left to right, we have a 15 and then a 7. We're going to add that to the third list. And so we've traversed the list in level order traversal, and each of these sublists are going to be put together into a single list, and then that's going to be our result. So that's what we want to do. We know that that's pretty straightforward. So the only question now is, do you know an algorithm that can do that can traverse it level order? And if you don't, the algorithm is breadth first search. So we want to run breadth first search on our tree and then add the values into lists. And the second thing to notice is, do you know how to implement this breadth first search? So we need to know this is the algorithm to use, and now we need to know how to implement it, and let me show you how to do that. So we have a tree and we want to run a pretty standard algorithm on that tree called breadth first search. And you
Oh, stole the list.
might know how to already implement this algorithm. You need a queue data structure because we're going to be inserting elements to the right, meaning we're going to, insert an element here, 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 right? We're going to be adding elements to the right portion, and we're going to be popping elements from the left portion. So as soon as so basically we're following first in, first out, right? The first element that gets inserted over here is going to be the first element that gets removed, right? So that's the order we're going to be doing things in. So the first thing we're going to do is take the first element, 3, and add it to our queue. This is basically to initialize the queue, right? And we know we're creating sublists, right? So what we're going to do now is see that, okay, count how many elements are in our queue initially, right? There's one element in our queue, so we're going to basically remove one element from our queue. We're going to see, okay, the 3 is in the queue. Now let's get rid of the 3 and add it to a sublist, right? Now the queue is empty, so we know that this sublist is complete, and what that tells us is basically we went through the entire first level, right? That's what we're trying to do. We're going through every level. We know that the first level only had one element in it, so now we're done. But when we pop that 3, we need to add its children, right? It has 2 children. It has a child 9 and a child 20. So we're going to add those children to our queue, and we're going to do it from left to right because that's important, right? We're doing this from left to right. So we're going to add a 9, then we're going to add a 20. Okay, so now we want to go through the second level of the tree, right? So we're going to have a sublist for the second level. Clearly, we have 2 elements in our queue. So we're going to basically pop these 2 elements from our queue from left to right. So the left is 9. We're going to pop 9 from the queue, add it to the sublist. So 9 is added to the sublist. And notice how 9 did not have any children, right? So we don't have to add any children for 9 into our queue. So next, we still remember we had 2 elements we were trying to remove. We have 2 elements in this level, so let's now pop 20, so we can add 20 to our sublist, right? So now, clearly, this level is complete. We added both nodes in the order 9 and 20 to a sublist. But notice 20 had a couple children. It had 15 and 7. So as we remove 20 from our queue, we're adding its children to the queue for the next level, right? Because we know we want to keep going down a level. So when we get here, the values will already be added to our queue. So 15 and 7 are added to our queue. We're done with the second level. Now time to go to the third level. We see that there's 2 nodes, 2 values in our queue. So we're going to pop both of these values. First we pop 15, add it to the sublist for the third level, and then we pop 7, add it to the sublist for the third level. Neither of these nodes had any children, so now we're done. We know we're done because our queue is now empty, right? There's nothing left in our queue. So we created a sublist for every single level, and as the question wanted us to do, we're going to package all 3 of these sublists into one list and then return that as our result. So we're really just doing a breadth first search algorithm with a queue on this binary search tree, and since we're doing it like that, the time complexity is going to be O of n. We're only visiting every single node a single time. The memory complexity is also O of n because our queue, at any given point in time, our queue could have up to n divided by 2 elements in it, because the biggest level of a tree could be n divided by 2. That's how trees work, binary trees at least. And so we know that n divided by 2 can be rounded to big O of n. So the memory complexity is big O of n with breadth first search. So with that being said, let's jump into the code. So first, let's initialize an array for the result. And we also, remember, want to have a queue. So in Python, we can do that with collections.dec. This will give us a queue, and the first value we want to initialize this queue with is the root node that we're given. So with that, we can start running the breadth first search, and we're going to run breadth first search while our queue is non-empty, remember? And since the queue is non-empty, we're going to get the length of the queue, right? So we're going to get the number of nodes or values that are in this queue currently, and we're going to loop through every single one of those values. This queue length is basically ensuring that we iterate through one level at a time. We're going through one level at a time. And with those nodes from that level, we're going to be adding them to its own list, right? And then we're going to add that list to the result list. So I'm going to loop through every value in this queue currently. So for queue length, I'm going to pop nodes from the left of the queue, right? First in, first out. And it's technically possible that the node could be null, so I'm going to have a check to make sure it's not null. Then we're going to take the node value and append it to the list level. And don't forget, this is also important, that to our queue, we make sure to add the children of this node, so node.left and node.right. Technically, these could be null, but that's why we have this if statement. So then when the next loop comes around, right, we come around to the next iteration of the while loop, it'll make sure to check that these nodes are non-null before adding them to its own level list. Okay, so now we have the loop in place that's going to iterate through every node of a single level. After we've done that entire level, what we're going to do is take our result and make sure we add every single level to that result, right? And then we're going to keep running this outside while loop, the outer while loop, until there are no nodes left in our queue. That's how we know we've gone through every single level, added it to the result, and then at the end we can finally return the result. And one last thing we want to do is make sure that if we're adding a level to the result, we want to make sure that level is non-empty. Because we know technically our queue could have null nodes. We're not adding null nodes to the level list, so we want to make sure that level is non-empty if we're adding it to the result. We can run the code and see that it does work, and it is pretty efficient. This is a breadth first search level order traversal of a binary tree. And we did it in linear time, and I hope that this was helpful. If it was, please like and subscribe. It supports the channel.
Right? Apparently, this is Traversal office. And you give the sound. Yeah, where did load come from? Okay, so Give yourself away. Sleep. Sounds good. Okay.